everyone. Sorry for the delay, rookie mistake. Today I'm giving a talk on Qutrit and Qubit compilation and some recent work in that, and I think it'll be of interest to the programming languages community because programming people like abstractions. First, I'll define a qutrit. So if qubits, in qubits you have a pure qubit state being some superposition of ket0 and ket1. And for qutrit, that's superposition of ket0, ket1, and ket2. So many physical systems already have this, and including in qubit devices today. So this is just a figure from some paper on qutrits in just trans1 qubits today. So this higher ket2 level state is already there, and you can have hardware operations that use it. In the qubit implementation is just you choose to be in the 0-1 subspace. So you choose to just stay in the 0 and 1 levels. What are qutrits and higher dimension qudits good for? Well, there's some hardware tricks you can do, such as mitigating leakage or improving noise thresholds or improving noise resilience in quantum communication. I won't go over those in this talk, but there's quite a bit of papers on that. You can also have qudit native algorithms. So for example, there's like some qutrit algorithm to find the parity of permutation of 3 things. And there's also emulation, which is when you do qubit operations using qutrits or higher dimension qudits. And I'll give a few examples on that later in this talk. I'll talk more about fault-tolerant qudit computation. The reason why I'm interested in that is because most people, I would say, believe that quantum computers must be fault-tolerant to be useful in the long term. And we're more confident about the long-term benefits of fault-tolerant quantum computing. And so many useful qubit things actually have prime dimension qudit generalizations, including Clifford's, which I'll give background for shortly. So prime dimension qudits, so any qudit dimension, which is a prime number, the Cliffords are efficiently classically simulable, just like it is for qubits, but just Clifford's isn't universal. So you need to add at least one non-Clifford gate. So this is what the generalization looks like in operator notation. So just what properties hold. So where D is the qudit dimension, x to the power of D is the identity, and z to the power of D is also the identity for single qudit gates, x and z, those generalizations. You also still have a Hadamard gate. This works only for prime dimension qudits that you can define a Hadamard nicely. And you also have Weyl-Braining relations about what happens when you commute z and x with each other. You also have the Clifford hierarchy, which also generalizes. To say what this x and z are, so the x is the +1 operation modulo d on the computational basis states, and the z does phase to the power of the computational basis state number, where this phase is the third root of unity. Oh, sorry, the dth root of unity. So for qutrits, it's e to the 2 pi I over 3. And for qubits, it's e to the 2 pi I over 2, which is just -1. So for qubits, this is what it exactly is. And then for qutrits, this is what x and z, poly x and z look like. You also still have your z and x basis states, which is your eigen states of these 2 operators. I'll show some circuit notation that we'll need to recognize some of these circuit diagrams later in this talk. So for qubits, you have your C0 gate that looks like normal, and then there's multiple qudit generalizations of the C0 gate. So there's a Clifford one, which I'll show next, but there's something I call ket2 controlled or singly controlled. And what this does is if you have your control qutrit in the 2 state, then it will do the target operation. Otherwise, if the control qutrit is in the 0 or the 1 state, then it's identity on the target operation. And notably, this is not Clifford. The Clifford generalization of the C0 gate to qutrits is this one right here on the bottom left. And this is a lambda label on the control. This was defined in a past paper to be applying the target gate to the power of lambda, so that many times. And you also have a C0 inverse because it's this gate is only self-inverse for qubits. There's in general, you can also generalize the X gate in more than one way. So for qutrits, there's 5 single qutrit X gates. The left 2 are the poly ones that are the +1 and -1 modulo D operations. And then the right 3 are just, for example, X01 is the emulation of qubit X gate, which sends 0 to 1, 1 to 0, and is identity on 2. So these 3 on the right-hand side are Clifford. Going back to this slide, for non-Clifford gates for universality, we need to add at least one non-Clifford gate to have a universal gate set. And we preferably want one that's conceivably gives fault tolerance to our gate set. So for example, these 2 support magic state distillation and injection, for example, and other ways to possibly implement fault tolerance. So the left is the qutrit generalization of the T gate, which is also a generalization for all prime qubit dimensions. And the right one is the qutrit metaplectic gate, or we just give it the letter R. And this one's also not Clifford, even though it looks as if it should be Clifford. And so the left one is the 3rd level of Clifford hierarchy, as is the case with the qubit T gate. And then the right one is interestingly nowhere in the Clifford hierarchy. And there's a lot of fun things I want to say about that gate that I don't have the time for here. This leads me into emulation. So one application that is quite interesting from a compilation or useful in, I guess, from programming languages perspective is the emulation application where you want to do a qubit gate, but using qutrits, and maybe you'll get some benefit to this. So this was perhaps one of the earliest examples of some kind of interesting qubit emulation that you can do with qutrits. So this is there's n control qubits, and you want to implement the target unitary U. And so this decomposes it into a bunch of qutrit Toffolis, and the fun part of this is that it's log depth. And it doesn't require any ancilla. A second example is that you can do the qutrit binary AND gate. You can do the qubit binary AND gate emulated on a qutrit Clifford +T. And this isn't possible with qubits alone because it wouldn't be reversible. That's why you need a Toffoli gate for qubits to do the AND operation on bits. And it turns out the decomposition is really simple. It's just this, which is a T-count3, qutrit T-count3. And to show its emulation, I printed out the truth table here. So the blue rows are the ones that are, if your input is 2 bits, and you don't really care what the gate does when the inputs it has at least one trit, so at least one in the 2 state. Another one, it's quite fun, is this is the qubit CCZ gate, and this is the qutrit Clifford +R gate set. So with an R count of just 3 single qutrit non-Clifford R gates, then you can do the qubit CCZ gate. And so this is a new, or as a few months ago, our paper on this, a lower new minimum of the number of single qudit non-Clifford gates to implement the Toffoli gate for qubits. And it is unitary too. As a last example, this one's not emulation because it's not a gate. This is a state. So this is an implementation of the 3-qubit W state. So the W state, the least number of qubits you can have in a W state, to call it that, is the 3-qubit W state. And this turns out you can exactly implement this in qutrit Clifford +T with T-count3. And I'm still trying to make the right-hand side a bit more interpretable. And you can extend this to any power of 3 number of qubits. Whereas in the qubit case, you can only do it for power of 2 number of qubits. So you would have to do some post-selection to get it down to the 3-qubit W state. So this is where we launch into the ZX calculus part of the talk. And the overall picture for this part of the talk is to know that we're going to give you a bunch of diagrams that hold for any prime qubit dimension. So this is a nice abstraction because underlying that, all the matrices would be like different sizes and have different definitions of the poly Z and X and Hadamards and all this stuff. But in the ZX calculus, you just get a single real set, and it generalizes to arbitrary prime qubit dimensions. So the first ingredient we'll need is the copy operation. So it's called copy because although there's no cloning theorem, this copies any computational basis state. So if you put in ket2, it'll give you 2 copies of ket2 out. And this is addition modulo d, where d is the qubit dimension. So the simplest example of this is like the CX gate. This is the Clifford CX gate for any prime qubit dimension. And then and so if you copy and then you add modulo d, then you exactly recover the CX gate. This is a typo on the right-hand side. The direction of the edges matters for qubits, but for qubits, it's symmetric. I'll just show 2 rules of ZX calculus, even though there's not that many, but explaining it would take a while. But so one of them, this is a screenshot from an upcoming textbook for high school children to learn quantum computing just from drawing diagrams. And so this is called the spider fusion rule because you can generalize those green and red dots with multiple wires coming out of them, multiple legs, to spiders, which can have any number of legs. And if you have 2 spiders of the same color connected by at least 1 wire, then you can smush them together and add up their phases. So in this case, there's no phases on them, but they fuse. And one other rule that is probably just most useful is the color change rule. So the color change is just another word for Hadamard. It's a quantum Fourier transform because these yellow boxes are the Hadamard gate. And then if you apply all Hadamards on all the inputs and outputs to a green spider, then you can change it to a red spider. And you can do the same thing with Hadamard inverse to the red spiders to get the green. So change between the colors. And so here is the rule set for ZX calculus for all prime dimension qudits as of a few months ago. And the circle part in the top left is the rules that we just talked about in the previous slide. And just showing you the rule set so you can see that any equality of linear maps any prime dimension qudit circuit, it doesn't have to be unitary, just any linear map on prime dimension qudit Clifford circuits, then if they are equal, then you could, in principle, find a series of these rules that can rewrite one of them to the other and vice versa. For qubits, this is known for even non-Clifford case, but we're still working on that for qudits. Just an example of what these rewrite rules might look like. So on the top left is the circuit diagram for a GHZ state for qubits, but actually it's the same diagram for qudits, just put in the appropriate generalizations of Clifford. And then on the right-hand side, the top line is the literal translation generator by generator. And then the second line is let's fuse spiders of the same colors together. And then the second to last line, you do color change, one more fusion, and then you get something which is much more useful to work with and conceptualize. You see that the GHZ state is symmetric with respect to each of the outputs, whereas the circuit one that we started with was unintuitive and doesn't say much. To get some flavor for useful generalizations we can do from qubits to qutrits in this case. So this is our work presented at QPL earlier this year. For qubits, we have these phase gadgets. So we saw some of these in the Lee's presentation because so this shows up as a key ingredient of the QAOA algorithm. It also is used to implement the CX gate on superconducting qubits. And we call them phase gadgets in ZX, but Matthew Amy and his group would call them phase polynomials. So what we tried was let's just take the qubit ZX diagram for phase gadgets and then just plug in the corresponding qutrit ZX version and see what we get. And so we get this equation, and so which seems like the generalization to the qubit case, from the qubit case to the qutrit case. The pink here is just because it's a nicer way to work with, so we don't have to care about the directionality of the edges, but in practice, it's the same as we could have easily converted to red as well. So in the next part of this talk, still in this part, we'll use the convention for labeling spiders with phases. So just to know what the underlying linear map is. For the green spider, it just means we're applying some phase to the one ket1's part of that sum and some phase to the ket2 part of the sum. So we're labeling by those two phases. And the pink spider is the same thing, but for the x basis states rather than the z basis states. So on the slide before that, we've proved something, but what kind of gate did we actually construct? Well, let's say x and y are computational basis states for qtrits. Then this qtrit phase gadget implements some phase to the power of x plus y mod 3. So we can generalize this to any arbitrary number of qutrits, and as shown on this slide. And why we're interested in this is because we want to build controlled gates from phase gadgets, or this is our interest, but there's many things you can do with phase gadgets. So for qubits, this is how to build a controlled gate from a phase gadget is to just stick on two single qubit gates on the control and target respectively. For qutrits, if you attempt that, you can't build any arbitrary ket2 controlled single qutrit z phase gate. So it applies the phase theta to the ket1 state and the phase psi to the ket2 state of the target qutrit. But if you do this construction twice, basically twice with permutations on the controlled qutrit right before and after that, then you can get any possible single qutrit controlled gate in this Heisenberg-Will ZX basis. And for adding multiple controls, that's going to be the last part of this talk, which I also think is quite fun to see. The construction on this slide, we're going to, in the next part of this talk, show you how to build these multiple control gates. But after showing that, you probably will be convinced that this construction on this slide has polynomial gate count, which is quite nice. So some background on multiple controlled qutrit Toffolis. I think this is like really recent progress because in the past, there were some deficiencies with the undesirable properties of past explicit constructions. So the naive one would be to have ON clean ancilla, so initializing the ket0 state. Another one could be to have uniformly controlled Gibbons rotation. So you have smaller rotations, the more number of controlled qutrits you have. Another one had qubit gates, which are pairwise on qutrit states. And there's a few that had gate count exponential in it. So for various reasons, these ones are not both efficient and conceivably fault tolerant. So that was the goal that we headed into. The next few slides, I just want to have a picture in your head of the left-hand side. I'm going to show you the qubit decomposition of some circuit, some multiple controlled Toffoli. And on the right-hand side, I'll show you a qutrit one that has the same structure of the circuit. So this left one is called the Slater-Weinfurter one from 1995, so a few years before I was born. It was actually thought to be impossible to generalize this to qutrits, or at least there's some paper that concluded that, which is quite interesting. But it actually is possible to generalize to qutrits, which is pretty funny, where this is for any qutrit unitary V. And notably, the useful part of this is that if you have V squared and V is self-inverse, then V squared is just the identity. So we're gonna use this. This is useful. This is another generalization where you have one borrowed ancilla. So this wire on the very bottom left with one input and one output, but this means that a borrowed ancilla means that whatever state that it comes in, you can return it in the same state as entered. You just need it to be physically connected so that you can do this gate more efficiently. So we generalize this to qtrits. It looks like this. So it's the same paradigm on the left-hand side, but now you do it 3 times. And this will work for any qubit dimension. Just do it d times. So that's pretty cool. The nice thing is that this is a polynomial gate count with the number of controls. And this was for quite a while in terms of, I thought about this a lot, we were interested in how to do this for a linear number of gates with a number of gates that's linear in the number of controls. So for qubits, in 2015, Craig Guinea published this blog post, which looks like this, and this uses a linear number of borrowed ancilla qubits. And we weren't sure if this was possible to generalize to qubits because this uses a kind of toggle trick, which seems kind of binary. But this is fresh off the presses. I just made this figure today, but this works. Where this, interestingly, this lambda control, it is the one that applies the power of the target gate to the target gate to the power of lambda, to the power of the control qutrit entering that lambda. So this is really cool. And you can see that if you plug in the qubit versions of the right-hand side, you exactly recover the left-hand side. So this lets you exchange any 2 trit strings efficiently and construct any ternary classical reversible circuit if you know how to do any kind of qutrit Toffolis. Wrapping up my talk. So here I'm just showing you that you can also multiple control, so trit string control, any type of Clifford gate, because CX, S, and H, they generate all the Clifford gates for qtrits and prime dimension qudits. So for qtrits, we just explicitly constructed these, and we use CX calculus to figure out how to construct them, but it might be a bit hard to see that this is indeed Clifford plus T unless we write it this way, but it's not intuitive this way. And I think the most exciting part of this was that we also realized that the qutrit trit string controlled version of the controlled T gate is really nice compared to the qubit case. The qubit case is terrible because in the qubit case, you have to either post-select or measurement uncompute if you're in qubit Clifford plus T. Or you have to add the square root of T gate to the gate set. Those are the practical ways of implementing the controlled T gate for qubits. But for qtrits, because T to the power of 9 for qtrits is the identity, so T to the power of 5 is just the T gate. So you can use T to the 5 as the square root of T, because T to the 5 squared is T to the 10, which is T. So you can multiple control the T gate and still unitarily only use qutrit Clifford plus T. So now we constructed CX, S, and H, and T all in qutrit Clifford plus T. Then you can control on any trit string, and by extension, any combination of trit strings, any qutrit Clifford plus T gate just directly, so exact synthesis. So this is not possible in the qubit case, and I think this is really nice for a programming perspective, because if you have any circuit that you have a Clifford plus T decomposition of, which in Clifford plus T is approximately universal, then to add any controls to it, so any if statements, that kind of stuff, then you exactly know how to build it. You don't need to figure out how to build it. In summary, we had different parts to this talk. We presented multiple controlled qutrit Clifford plus T gates, and you can do that efficiently in qutrit Clifford plus T. You can build any diagonal qutrit gates in qutrit Clifford plus T, and a lot of the proofs for a lot of these constructions generalize to prime dimension qudits or qudits, depending on which ones. So that's quite a nice abstraction. Thank you very much for listening to my talk.